The digital transformation of urban mobility use case aims to demonstrate how Rainbow system will contribute on developing a real-time geo-referenced notification system for vehicles traveling in urban areas about hazardous situations. The Rainbow platform will also act in the vehicle communication field by providing a reliable and decentralized approach to safely handle exchange of messages. The Automatic Hazardous Event Detection System is the name of the service implemented for this mobility scenario. The use case depends on a real-time georeferenced notification system for vehicles traveling in urban areas about a hazardous situation for the city mobility network due to any possible causes, accident, failure of road infrastructure, animals on the road, wrong way driving. The notification system is designed to collect signals issued by entities in urban areas. There are two types of notifications. Explicit notification that refer to those that are either triggered directly by citizen or automatic notification that are triggered by onboard sensor or by roadside units. Each alert signal is delivered with the available geolocation information, allowing reports to be localized in the areas where the hazardous situation was detected. In the use case definition, the following systems are involved. MIC node, based on ETSI multi-access edge computing paradigm, is a point of computational and data storage, one or two hops away from the mobile client to meet the response time constraint. Edge device, it is identified with all end-user devices, vehicle equipped with communication capability or smartphone. Fog node, it is identified with the roadside unit, which is a small point of computation and data storage, connected directly with the road infrastructure. It is a small, lightweight, and IP6 device with different power consumption profile based on its CPU performance. Cloud node, identified as a generic server in the cloud offering computation and data storage services. As a starting point configuration, the demonstration consists of a road-equipped segment with the on-site installation of a roadside unit. The infrastructure is equipped with an IP camera directly connected with the roadside unit. The video stream is also reachable by the MIC node, which communicates with the roadside unit. The service consists of a series of computer vision techniques and AI algorithms able to identify the presence of animals on the road, which can represent a dangerous situation for drivers. Based on this, the service can run either on the roadside unit or on the MIC node, where each configuration implies advantages and drawbacks with respect to the latency and accuracy constraint. Indeed, the roadside unit benefit of the direct connection with IP cameras, which yield a high-resolution video stream at a high frame rate. The higher the resolution, the more accurate the result. At the same time, the service requires high computational power to run on the roadside unit. To achieve this, must increase its power consumption, which may cause the overheating of the system and malfunctions in the road infrastructure. On the other hand, the MIC node does not suffer from overheating problem, since it is a powerful computer typically hosted in a place equipped with an efficient cooling system. We will not have problem running complex algorithms. Unfortunately, due to the channel latency and the available bandwidth, the node works typically with a low quality video stream with smaller frame rate. thus resulting in less accurate results. Besides, the quality may change due to the variable network condition. Moreover, once the hazardous event has been detected, the MIC node must communicate it to the roadside unit, which is one equipped with required communication hardware able to communicate it to the incoming connected vehicles. Finally, as explicit notification, a road user may spot an hazardous situation on its own. He may decide to signal it through the dedicated citizen app. The use case scenario is based on ETSI standard for V2X. The V2X hazardous location notification DENM messages with animal on the road subcode is used. There are several cause codes in ETSI standard, starting from roadworks, adverse weather condition, and some hazardous location codes, surface condition, obstacle on the road, and animal on the road. In particular, the hazardous location animal on the road details the type of animal, for example, wild animals, the size of the animal together with the position on the road. Those kind of messages can be received from the vehicle point of view, both by the roadside unit through the V2I communication, vehicle to infrastructure communication, or through the V2N communication, vehicle to network communication, using the MQP message, with the V2X message as a payload. This is the architectural design of the service that is composed by four main subsystems: vehicle, roadside unit, MIC node, and cloud node. The connected vehicle is a vehicle equipped with a CV2X communication device and a V2X client. V2X stands for Vehicle to Everything Communication. The vehicle performs data acquisition from the onboard CAN bus and dispatch it to a cloud using ETSI CAN messages through the AMQP protocol. CAM stands for Context Awareness Messages. The vehicle also receives ETSI DENM messages from fog nodes via PC5 interface or via the network interface. The messages of interest for the vehicle are the hazardous location notification messages with different cause code depending on the type of the hazard. When the vehicle receives DENM messages from the fog node, it parses and displays them on the HMI depending on their relevance. The main components on the vehicle are PC5 and UU mobile protocol stack. Each manage the UU and the PC5 communication layers. The MQP client, it establishes a logical communication with the MQP broker on the cloud node, and it extracts and encapsulates V2X messages. The MQP protocol is a publish and subscribe protocol. V2X management, it handles the transmission and reception of the CAM and Dynamo messages. The HMI displays the message to the end user according to the relevant policy. The fog node is the roadside unit with a PCI interface and equipped with an IP camera and a GPU AI computer. The fog platform includes an IP camera able to perform AI computer vision tasks and to communicate with vehicles both through the PC5 communication and AMQP messages via cloud. On the computer vision side, the platform manages the video stream data, gathering and forward them to the MIC node. Moreover, it can run AI detection algorithms based on rainbow orchestration decision. On the communication side, the fog platform is in charge of broadcasting hazardous event notification through HCDEM messages via PC5. It also acts as an MQP client, publishing messages on the hazardous notification to the cloud so they can be accessible everywhere and not only from vehicle in the roadside unit coverage area. The MIC platform will receive data coming from edge vehicles in the form of ETSI-CAM messages. Those messages can be used to be processed together with the data coming from cameras. The fog platform is also responsible for the creation of a trusted overlay of fog and MAC nodes. The MIC node is a node that simulates an edge server typically installed inside a mobile operator network. The MIC platform is typically hosted in a mobile operator network. The MIC node can run the AI detection algorithm thanks to the video streams received by the roadside unit. The MAC node can notify hazardous situation to the roadside unit that will broadcast them directly to the vehicle via PC5 communication, and to the cloud node, where they can be retrieved via mobile connection. The cloud node aggregates contextual traffic data coming from vehicles, local traffic control center, or citizen. The cloud can let implicit alert signal issued by vehicles in urban areas. The aggregation platform will expose API through a southbound interface toward the fog platform. The Citizen app allows citizens to alert the municipality about hazardous situation on the road. For the final demonstrator, the Rainbow monitoring agents collect the following metrics: the average power consumption, that is the average of the current absorbed by the roadside unit over 5 minutes. Network bandwidth, megabyte per second, is a measure of the network latency between the IP camera on the roadside unit and the edge node. The event base is a detection of an event from the edge node for more than 3 consecutive frames. The collected metrics are used to trigger the service level objectives. Based on the derived metrics and SLOs, the orchestrator moves the service on the high power fog node only when it is required, while using the MIC server during every other moment. To provide the correct metrics to Rainbow, Python monitoring library was used. The defined Rainbow scenario for the use case are more challenging in the final demonstrator compared to the early demonstrator because the scenario involves a real on-road components and the orchestrator latency becomes a critical factor for the success of the demonstration. The scenario number 1 is the fog to edge service orchestration based on roadside unit power consumption. This scenario aims at demonstrating how Rainbow can orchestrate services with the goal of saving power energy. The second scenario is the edge-to-fog service orchestration based on bandwidth occupancy. The scenario aims is to demonstrating how Rainbow can contribute to an efficient and reliable bandwidth usage. The third scenario is edge-to-fog event detection. This scenario aims to demonstrating how Rainbow can contribute to an efficient and reliable usage of the edge computing while a dangerous event is detected. It is important to remark that in all scenarios it is mandatory to maintain at least one instance of the service at any given time instance.